in my screen. Can you see the presentation and the terminal?
Yes, we can see both.
Okay, thank you. Yes, let me see. Okay, so I will start slowly on this part. So we will look at the basic concepts of parallel computing and integrated with Python, right? So we will cover these questions here as parallel computing, the different parallelization mechanisms that are available for Python, how to implement this in Python code, and also how to deal with our HPC centers with this parallel programming with Python. But notice that this will be very basic, right? I will show you basic examples, and the important point is that you get some general concepts and general ideas that later on you would apply maybe in your research, right? So here there are some prerequisites that you need to follow in order to run the test cases that I will show you. Yes, and we prepare some requirements for HPC2N, UPPMAX, and Tetralit at NSC. Notice that the versions of the modules are different, right? And also the way to create the environments at the different centers. And some packages have different versions that you will see here, for instance, specifically for Julia. So we will see the version 1.9.3. And at NSC, they have a different version for Julia. And the way to run the script is a bit different. Yeah? So here, for instance, we can follow the instructions at UPMAX specifically. And if you have questions on the others, you can let us know. Let me see. Here, I can copy the instructions for UPMAX. So I am sitting here at the UPMAX terminal. So we load the module, and then we create the environment with the Python -m VM and the Python course. Yes. So here you create the environment. So I cheated a little bit because I did it before this lesson, and that's why, and that's because you need to some time to install the modules as they are listed here. So once you create the environment, you activate it by running source, the path of the environment. In my case, it's present in this directory. That's why I can do the source VM and then bin activate, and then it will activate the environment. Yes. So I have activated that. Then I install Numba. This is required for the Numba examples. And for running MPI in Python, you need to install this MPI for Py. And this is the required tool chain that you need to load. For Julia, the Julia version at UMax is this one. Yes, there are others, but the examples are tested with this version. And for the Julia example, you also need to run the Python on the terminal and then import Julia and then run this Julia install script that should be available on the Python session. So there are different schemes for parallelizing a code available in Python, right? This lesson is I would say, more advanced in the sense that you first need to have a running code in serial mode that gives you the correct output. Yes. So once you have your serial code, and you notice that it is taking some time, yeah, then you can proceed to do some optimizations and also start thinking about parallelizing your code. But before that, I would recommend to try to parallelize and to do any optimization because first of all, you need to have a working code, organized code, I would say, and then after that point, you can start parallelization because you are adding another level of complexity and it's difficult to debug. It's more difficult to debug in parallel mode. So here I show you one simple example. And this is a 2D integration. You can see here that there are one integration in the X axis and one in the Y axis. And this is a good problem to start with because we know exactly the output, which is zero, right? So we can test our different parallelization schemes by running this serial code. So I did a naive implementation of this code. And this is how I would do that in other languages by using two four nested loops. So here I am doing the discretization in the X direction and this in the Y direction, right? These are two for loops. And in general, this is expensive in languages like Python, R, like and that's why we can do some optimization in this part. So more likely, if you are expert in Python, you will see that this is not the correct way, but this is the way that I will use because this will be a test case to do the optimizations later on. So here we send the return for the integral after doing this two loop, two nested loop summation. Yeah. So then I call the integration and I do some timing with the perf counter function and print out the results. So this is very naive, I would say. This is an initial optimization. And then I need to test if that works properly. So one way to work with this script is by copying that, then go to your terminal and open your editor, for instance, integration to the serial. So I did it already, and this is my script that is on the Rackham machine. Yeah? So this contains exactly this example here. So then we can test it. And to run the script, you can write your batch script that it has been mentioned. And I am doing a shortcut for this, and I will use it run to run the integration, the Python script. And this is done by using this format. srun, the name of the project, which is this project here, project ID. Then I will request one task for this because it's just one program that I need to run. The time is, in this case, 10 minutes. And then I start running Python. So this will allocate a job in the queue. Yeah. So I run it, and you can see that it is assigned a job ID, and then it's waiting for resources, and then it will When it starts running, it will tell me, and also it will output the result. So this is a serial job, and previously it took 20 seconds to run, right? And for this case, it took 23 seconds. So if you want to get statistics, then you are you should run this script several times to get more reliable results. But just for one, it's about 20 seconds. So then in our code, once we have our code, notice here that I enclose the expensive code in a function, right? That this is also a good practice. We need to enclose the expensive code in some functions to track the timing for that part only. So in this case, it's simple. I know that this part is the expensive part. So here is where I can proceed to do some optimizations. So I know also that the code is working. Yes, it's relatively straightforward to get it, but some other times it's not that easy. So it's great that you ask about this, and I can go in more detail about what this code is doing. Yeah? Thank you. Yes.
Yeah.
Yes.
Thank you.
Yes. This is the problem, right? We need to perform this integration, and this means a summation. But if you look at this expression, this is continuous. Yes, this is a continuous integration, but we can approximate this summation by doing some discretization in both the x and y direction. Yeah? So we cannot do the continuous summation because it's not possible with computers, but we can discretize the x and y directions, and then we can do a summation here for the x, and also then we can do the summation in the y direction. That's why we need two indices for the x and y, and that's what we are doing here in the x direction for the x I index, and for the y direction we are running the j index. Yeah? And if you look at this and you do this with numbers, you will see that it will goes from 0, uh, yes, from 0 in Python, and then you can see that it starts from I from 0, then it will take the value of 0.5, and this will be multiplied by the size of the grid, because then each index will refer to one bean in a two-dimensional array. Yes. And essentially, this is solving this part, right? And you need to also to set a bean size. So this is how the equation is translated into the code. We also need a discretization in the y direction, and we need to accumulate the partial summations in this variable my sum. So, but remember that we are doing the integration without the bin sizes, and that's why we need to multiply by the bin size in the x direction and the y direction, because it is the same, it is x, it is h, so that's why we need to multiply by h squared, which is this thing here. Yeah? So this is the function, and then we take the timings and we summarize here the timings. Yeah? So, okay, so now we have this function, the initial implementation. We know that it works because it gives us the integral value, which is close to 0, yes, and the error is close also, is very small. And then we have an initial timing. So the goal in our program in parallel computing and in optimization should be to decrease this initial time with some other implementations that are available in Python. So, okay, so before going to the parallel part, yes, which I can anticipate something here, is that here we can distribute the work that is being executed here across several cores, right? In our machines, there are several cores, and also in PCs or standard laptops, now they are shipped with several cores, and then in principle, this can be distributed and executed across several cores so that the job is sent to the course, and then this should take, in principle, less time. Yeah, this is the goal of parallel computing. But before going to that, you need to know that in Python, there are several ways to optimize the script before moving to parallel computing, which, as I said previously, it adds another level of complexity to your code. So so what can we do then to make our code more or faster? We can use a Numba, and that's why we install a Numba in the requirements. You can follow them. The requirements are at the beginning of this lesson, and then you can use Numba, and it has several modules, several functions, and one of them is the ngit. Yes, and we can use this to decorate our function. Yes, if you remember previously, in the previous example, we used the integration serial function, as you can see here. Yes, and we took some timing, but we can use the ngit as a decorator, right? And then we can call the integration to this serial, but by using this method ng. Yeah. And then we can take the timing. So we can copy again this function. We go and paste the value or the text in our file serial number.py. So it's here. And then we can run the script. Let me see. In this case, this is serial, but with number. So, and I ran that before, and you can see that now the code takes 1.9 seconds. Yeah? So, oops, there is no number here. Interesting. And I ran that previously, and it took 1.9 seconds. If you remember, the initial time is 20 seconds, around that, yeah? Depending on the architecture, and also you need to run that several times. It's interesting here. So let me see if it is installed properly. Okay, so now you can see that in the present case, it took 7.4 minutes, right? The second, sorry. And previously, in a different architecture, it took 1.9, yeah, and it was in this case the speed up was around 10 times, yes, from the initial one. So just by using the decorator, you can get some initial speed up. Also, and this is also more advanced. So imagine that you already know some lower level language like Fortran or C, and you can write the expensive part in that language, and then you can call the libraries or the APIs that you obtain with that language in Python. Yeah. So in this case, in the present case, I know that the integration, the two for loops are the expensive parts. And I know that I write that in Fortran. And here I rewrote the function, but in Fortran, right? And this language is faster, right, in general than Python. So that's why I have this initial Fortran function. And the drawback is that you need to know how to program in Fortran or C++. Yeah? So I can copy this function, let me see, Fortran function, and it's there already. Yeah. So I copied that and I have that on Rackham. So now I can compile the function. Yeah. I compile the function. And I need a script to call the function that I created. Yeah? So, and this is a Python a script, as you can see here. So in this part, I am calling the function that I compile with Fortran. Yes. So instead of the initial function, I am using the compile code with Fortran. So again, I can call this Fortran code, py, and it contains the call to the Fortran function. So this is the way to import the function, yes. And once you compile the function, you will see that this API from Fortran is already there in the folder. So, and this name is the one that it is used in the call Python script. Yeah. So this is something that you can do. And then if you run this code, it takes about 1.3 seconds. So you get something useful from this workflow, right? But the problem is that if you change the Fortran code, if you need to do some changes like the ones I mentioned here, imagine you need to do some changes here, you need to change the integration or some variable or something else, then you will need to recompile the code every time that you do that. So this is one drawback, yes. And in order to avoid this part, you can use another language where you don't need to recompile the code. And in this case, I only mentioned the Julia language, which in general is faster than Python, yes. And here there is an example. You can copy this script and then do something similar, write this on the Rackham. So this is the Julia script. And Python has integration with several languages. We have seen that it can be integrated with Fortran, C, C++. It can be also integrated with R if you like R and you have your R code. So then you can call another language, in this case Julia, and you can call that within Python. So copy this script and then place that, for instance, in Rakan or Kebnekaise. And then you can run this in a similar manner as before. But in this case, the name of the script is Carl Julia code.py. Yes. You can see here that the time is reduced compared to the initial Python script. Oh, this is interesting. There is no Julia, but it should be there. It should be there. So, okay, so I will not go into this installation. Usually there's something happens to my environment, but you can see that once you set your environment and you call Julia, then you can see some speed up, right? With respect to the initial time. And the good point from Julia is that you don't need to recompile the Julia code, yes, but because this is not a compile-based language. It is just a interpreted language similar to Fortran. And even though you can get some speed up. So, okay, imagine that we exhausted all the ways that we can optimize our serial code. And up to this point, we haven't used any parallel tool. And then we need additional performance, yes? Something else need to be changed in our code to get further speed up. And Python has already some ways to parallelize the code. And one of them is called the threads. I won't go into more details about this because this is very specific and this is used for some specific task like input, output, handling of files. And this is because it has an issue with the global interpreter that in general serializes the code. So if you try to run your code with the threads, you will see that in general, for computational expensive parts, it takes a long time. It's similar to the serial one. So that's why I won't go into uh, deep mode here. So I will just mention that. So it's very specific. But another way to get some parallelization in your code is by using some explicit parallelism. So if you're using packages like NumPy, right? Then behind the scenes, yes, as a backend, they are using some library for the linear algebra that can be OpenBLAS, FlexiBLAS, LabPack, MKL, right? And you can see the information of what libraries are being used. If you type a NumPy a show config in your Python script, and this will tell you what library is being used. So here, for instance, there is a simple example for the matrix multiplication and how you can see the speed up, right? So if you're computing this type of operations many times, then you should know that you can set the number of threads or workers, and this can be done with this variable here, right? Here I am setting the number of threads. For instance, here on the terminal, I can set the number of threads to 1, yes. And then I need the Python script. You can see this here, it is this part here, the file. And I can run the script as previously. And here I need to specify or distinguish between the task, which each is N1, and the number of threads. which in this case is 1 because I am specifying one thread. So notice the difference between -n and -c. Yes. So then for a previous run, it took 1.14 seconds. And for two threads, when I changed it to 2, so the time is reduced by about the half. So you can see here that it took 1.42 seconds. But if I use two threads, I also need to change this value here to use two cores. So it should take in principle less. You see, take less, but it's not that lower as on this other architecture. So you can see here that you don't need to change your code because the parallelization is already included in these libraries. And you can take a look at what libraries you're using. Sometimes the packages have already some implicit parallelization. Yeah. And the only you need to do is to set the number of cores or the number of workers by using some flag, as in this case, and then you can get the speed up. Yeah. So, but other times you will need to modify your code yourself and explicitly, and there are several ways. For instance, here this is more specific, but for the Fortran case or C++, you can modify your code to include some parallelization scheme. In this case, is OpenMP. So then you modify your code in an appropriate manner. Here I use some OpenMP instructions. Yes. Then you need to recompile the code. In this case, I added this OpenMP flag. Yes. To make your code aware of the OpenMP parallelization. And after that, you call the code by using a similar call script as previously, but you need to modify the code by using the external flag. In this case, for OpenMP, is this flag and this number of workers. So you can see that the time is reduced explicitly on this architecture that I used before. So the previous case, this one here for OpenMP, was for a shared memory. Yeah. So in the current machines that we have at our clusters, the cores, yes, share some memory, and parallelization schemes like OpenMP take advantage of the shared memory. But if you want to scale your code across different nodes, right? If you want to make your code, for instance, scalable up to 1,000 or even further number of cores, then you will need something else, not shared memory, but distributed memory. In this case, this distributed memory can be also done with Python, and you can use the distributed package. Yes, you can see here the multiprocessing package, sorry, but to perform the distributed parallelism. So here I imported multiprocessing. Yes, in Python, you don't need to install anything for multiprocessing because this is part of the standard library in Python. Then I imported this method here, array, and also the rest of the stuff for the performance counting. So one thing about parallelization is that you will need to change most likely the programming paradigm that you are using. So you remember in the first example that I used for the serial integration, I had two loops that run over the entire range, right, of integration in both the X and Y direction. But if I want to perform the parallelization, I need to change this way to think of the program, right? So in this case, I am using some specific parallelization where only the first loop is being divided across the different workers. Yeah. So how can I do that? I know the workload, which in this case is the number of iterations. And I also know the number of processes that I have or the number of workers that I will use. Yeah. And because of that, the workload will be the total number of integrations divided by the number of processes. Then I need to specify the beginning of the integration range, and this will be covered by doing this operations here is the workload times the process index. Yes, each process will have an index, and then it will end at the workload times the process index plus 1. So you can see here that by doing this division of labor, each process will have some integration range. Yeah? So now we will need some variable to accumulate the partial summation from each process, and this partial value will be accumulated in the partial integrals. Yeah? So we don't have now a total summation, but a partial summation for each process. And this will be accumulated in this array. And just at the end, yes, so we will collect the total summation. So here we generate the processes by using the multiprocessing process method. We call the function, and these are the arguments of my function here, yes? And then we start the processes. After they finish, we join all the processes, and then we collect the total summation at this point. Yes, we reduce the array for partial integrals, and we collect that into the integral, and then we take the timings here. So you can see here that the time is reduced from 20 to 6 seconds. Yes. And here we can use another approach for distributed computing, which is called message passing interface, MPI. This is a standard. And this is different from the distributed or the multiprocessing module that we saw in the previous case, because here you need to do the installations that are mentioned in the requirements part in the beginning of the lesson. So, but if you go to MPI, you will see that the paradigm for programming is similar because you need to divide the work across the different workers. Yeah. So you see here that we also have a begin and the end. Yeah. And we divide the work, we collect the partial summations, but the reduction and the and collecting the results is different in this case. We use a reduce operation that is given in MPI. So these functions, so these calls are included in the MPI for Pi module, and that's why you have to install this at the beginning. Yeah? So the way to run this script is by using MPI for Pi, MPI and the number of workers, and the Python interface and the name of the script. So here you can see that the initial time is also reduced. So how to run that? You collect this script here. I did it previously on UPPMAX, for instance. You need to change this project ID, the number of workers, and you load the modules as they are here, source the environment with the location of the environment, and then you use MPI run with the number of workers that are given here. Yeah. The last point that I wanted to mention today is the monitoring of resources usage. So you can see that for parallel computing, you can set some number of cores, some number of tasks, and it is easy to oversubscribe the resources. So imagine that here in my script, I specify four tasks, but when I am trying to run the script, I forgot it and I set to 40, right? So in this case, you are generated 40 tasks that we will try to run on four cores only. And this will easily oversubscribe the system, the cores. Also, imagine that inside your script, you set some MPI task, but at the same time, libraries that were mentioned previously, like in linear algebra, are called, and then you're specified only four tasks here and four here, but inside the script, the implicit libraries are also generating internal tasks, and this will oversubscribe the system as well. So that's why we have some tools to monitor the resources. And this is specific for Kebnekaise, but there are other tools at UPPMAX. In UPPMAX, something that you can do is to create an interactive session that it was mentioned previously. And then you can run the top command, right? Where you can see how the resources are being used at that point. Yeah, or H tab, for instance. And then you can monitor the resources. Here is the interface that you get on Kebnekaise. And here on the terminal of Kebnekaise, you type a job usage. Yes, that is available only on Kebnekaise, I would say. And then the job ID, this is the number that you get when you submit the job with SBatch. Yes, and you can see a number. This is the job ID. Then you can collect the URL that you get and paste it in your local browser, and you get this interface here where you can see the utilization. If you oversubscribe the resources, then you will see a red line going up, and this will cause some issues to our system. That's why it's a good tool to monitor the resources, and it provides information about the CPUs and the GPUs. So I am over time, and I will mention briefly that I have prepared two examples, right? One to inspect how to run the code that was mentioned previously for the 2D integration in an efficient manner, yes, and how to monitor the resources. And also this is a bit more advanced, but also something useful that is very common in workflows for Python and R, for instance, where you have a data frame and you need to perform some operation. So here I show you how to divide these operations across different cores, and this can be useful in a more realistic research problem, I would say. So if there are any question at this point before going for lunch? Let me see the chat. So the F2PY is available once you have MPI for Pi and also the NumPy available. So it will be available on your on your terminal. Like, FUPY, yes. This is on Rackham, for instance. And this is oops, FPY, right? No. So, but it's available on the terminal once you load it. Yes, the MPI for Pi and also the NumPy. Yeah, that's correct. What I show you here in the pre-requirements is some way to get the MPI for Pi, yes, if this is not available in any bundle and you want to do it yourself. But be aware that we have some bundles that where many packages can be present. Yeah? So if you have any doubt about how to locate MPI for Pi, you cannot do it by yourself, and you have struggling with that, so you can let us know. Yeah? Because even for other packages, like R, for instance, uncommon modules are available in these bundles. Okay, we can go for lunch. Sorry for